welcome back. This is the last talk of this session. Please welcome Chris Zaharia, software engineer at Q Control with a passion for quantum computing, neuroscience, and machine learning. Today, he'll show us how quantum algorithms can simulate the tiny Nematode C elegans and what that means for the future of AI.
All right, thank you. Yep. Thanks, everyone. Thank you. So yeah, I'm, as David said, a software engineer at Q Control. They're a quantum technology company. And today, I'm going to show you how you can use reinforcement learning with quantum algorithms to train a nematode worm to find food, both using a quantum computer simulator, but also with real quantum hardware devices. So first, I'll just do a quick introduction. So I posed the question, can we simulate biological brains on a quantum computer? We're going to use the C. elegans nematode as our agent in this example. So it's just a simple organism with 302 neurons. And we're going to find out if we can use quantum circuits to potentially map out brain behavior of the nematode. And we'll do all of this in Python. So why the C. elegans? For a tiny worm of only about 1 millimeter in length, it displays a surprisingly rich set of behavior. Its entire connectome has been fully mapped, so that's 302 neurons and about 7,000 connections. And due to this, the C. elegans is used in many different research studies out there. And also, its brain is at about the scale where we can start imagining mapping it to quantum circuits on current quantum computer hardware, which are in around the hundreds of qubits right now, and they're just starting to approach the 1,000 qubits size. And this is just how its entire connectome looks. One other topic that I'll cover as well before jumping into the project is just a quick primer on quantum computing. All right, so what is quantum computing? Everyone will be familiar with bits as being either one of two states, 0 or 1. Now, quantum bits, or qubits, they're somewhat different. They can be in multiple states simultaneously until they're measured. So when you measure them, then they'll collapse to either 0 or 1. And also, quantum computers aren't necessarily faster than classical machines. They work differently. So instead of checking one possibility after another, you can manipulate many states at the same time. And that's what gives them potential advantage in certain areas, like in simulations and optimization. So I'm going to first go over some key properties of qubits. The first one is superposition. So that's where a qubit can exist in two or more states at the same time. For example, both on and off at the same time, or maybe an electron in the ground state and in any number of excited states at higher orbitals, for example. One key aspect of superposition is combining waves to create new waves. So for example, when two waves overlap, you can either add them together or cancel each other out, and that's called interference. So quantum computers use this effect to amplify the probability of correct answers and suppress the wrong ones. The second property is called entanglement. Now, entanglement is often billed as the spookiest part of quantum computing. Really, it's just a deep correlation between qubits. So one analogy is you have a pair of shoes. You've got maybe the left shoe with you. You know that somewhere around you, there's the other shoe, the right pair, no matter how far away it is. So entangled qubits kind of share a relationship similar to that, although richer and in surprising ways. So they're not fully independent of each other anymore. And then the last property I'm going to cover is measurement, which is probably one of the funkiest aspects of quantum computing. So as long as you don't measure the qubit, it exists as a combination of possible states at the same time. But once you measure it, the qubit collapses into a definite classical state. So that's either 0 or a 1. And that's the only result you can actually record in reality. So the trick is to design quantum algorithms so that when that collapse happens, you get useful answers, more likely than not useful ones. So quantum circuits, they represent quantum algorithms as a sequence of quantum gates, so kind of like logical gates in classical computing. But instead of being limited on discrete on-off operations, these gates are continuous. So they rotate, they transform qubits in very precise ways. So for example, there's a Hadamard gate, which puts a qubit into superposition, a C0 gate, which entangles 2 qubits, and rotation gates, which adjust the qubit states by a certain angle. And at the end of the circuit, we measure the qubits, and that measurement collapses into classical bits, which we can interpret then as normal data. So parameterized quantum circuits is at the heart of machine learning in quantum computing. So instead of using fixed gates, we use gates with adjustable parameters. So these are angles that we can tune, just like weights in a neural network. So by changing these angles, we can change the way the information flows through the circuit, and we can train those parameters to maximize rewards in, say, our learning strategy. So that animation on the right shows a simple case with 1 qubit. So right now, you'll see there's an x rotation of half pi, then there's a quarter rotation on the y-axis, and then a quarter pi as well on the z-axis. And then in larger circuits, we stack many of these parameterized rotations across multiple qubits and layers, and then we often combine them with entangling qubits. That left diagram is an example of that. And that's what makes these kind of circuits, these parameterized circuits, so flexible. They represent a wide variety of functions, and we can optimize them using gradient-based methods, just like we do with neural networks. Let's quickly go over some use cases where quantum algorithms have shown potential advantages over classical ones. This is in simulations, like in drug discovery and new material design. This is in optimization kind of problems, like a traveling salesman problem for logistics. Machine learning for pattern recognition, and what we're going to discuss today. This cryptography, such as in encryption and cybersecurity. Finance and risk, like fraud detection, derivative pricing. There's also in search as well. So there's an algorithm called Grover's algorithm, for example, which solves unstructured search problems with a quadratic speed up over classical approaches. But quantum computers today are still very noisy. Real hardware suffers from decoherence, so the qubits lose their states really quite quickly. And there's also gate errors to keep into account as well, where operations aren't usually perfectly reliable. So that's why getting results from real devices often differs from what you'd get from a quantum circuit simulator. So if you look on the right, where this is kind of like a timeline, and we're in that middle phase right now, which is the NISQ, or the noisy intermediate scale quantum era. So before the latest quantum hardware, devices we have kind of coming up with lately, we're in the classical era. And then once we pass this noise era right now, we're going to enter the quantum era, which is where we will get quantum advantage. So quantum hardware will be potentially cheaper, more powerful combination than potentially classical hardware out there. So right now, to get useful results in this current regime, these error suppression tools are quite critical, which is one of the areas that my company, Q-Control, specializes in. So I'm going to get into the project itself. All right, so this is the simulation flow for a project. It's kind of usual kind of reinforcement learning problem. The agent lives in a 2D grid. There's food, and there's sometimes obstacles in the way. And just like in biology, the agent senses its environment. In our case, the nematode senses things such as chemical gradients that are emitted by its prey, like bacteria that it would consume. and also the direction of that it detects. When we extract, then we extract these features from its raw sensory inputs, and we turn them into a form that the agent's brain can understand. And then finally, we make a decision that could either be using a classical neural network or a quantum circuit that acts as its brain, and then it outputs an action to take. And in the second half, you use that action and execute it. So that might be moving the nematode in a certain direction or staying in place. Then the environment itself will update to reflect that action. So the agent's position may change, or it may collide with an obstacle, for example. So after each step, the agent will receive feedback in the form of a reward or penalty, and that's how we kind of drive its learning process. And then using that reward signal, we updated the brain's parameters, whether that is neural network weights or quantum gate angles, to improve, hopefully, its chances of success next time. And then we just continually run through that loop until either the agent finds its food or we run to a maximum number of steps to stop the simulation. This is just an example of that loop in action. This is mostly just setting up parameters before we do an execution against its brain. And this is just the second half, which we run execution, so it might move the agent in the environment, and just do a few other things, maybe post-processing related. This is how its reward function looks like. It's pretty straightforward. We reward the agent as it approaches its prey, or penalize it if it moves away from it. We scale the reward depending on how fast it finds its prey. We also add some additional rules around penalties, such as penalize it if it revisits the same spot or gets stuck. So altogether, we use all these signals to kind of adjust the agent's behavior, try to balance exploration and efficient goal seeking. So this is how the Nematode agent works today. It's got a number of sensory inputs, external and internal. The main one is chemotaxis, which is kind of detecting chemical gradients in the environment, which is similar to how we smell food. And then internally, there's just a way to track its hunger level. So if it finds prey, it's full. If not, it tries to find prey. And then all of that goes into all those features get encoded into the brain. In this case, a parameterized quantum circuit. And then we output that into maybe an action, like again, moving or staying in place. Or if it's in the same block as its prey, it would feed on it. One of the other purposes of this project was to kind of compare a quantum approach with a classical-based one. So I'm just going to quickly explain the classical agent that we use for benchmarking. So the classical agent just uses a simple multi-layer perceptron neural network as its brain. It's trained using a policy gradient method called reinforce. So that means it learns by increasing the probability that its actions, good actions lead to better rewards, or decreases the probability of taking actions that don't help it find its reward. And instead of updating at every step, we found that if we just use the trajectory of a certain time frame, say it's using its state, certain other variables like actions and rewards, that we kind of feed all that into episode blocks, it will train better as well. So we just update its policy at the end in blocks. And to make its training also more stable, we use baseline subtraction, which reduces the variance of how it learns by comparing those returns against a running average. And also, we add an entropy bonus as well. So basically, that encourages the agent to keep exploring, so it doesn't converge too early to a learning pattern that kind of gets us stuck, maybe to a local minima. So altogether, follow these steps. The strategy here helped us, just using a pretty small neural network to kind of create an effective learning strategy for it to navigate in this grid environment. This is just a simple example of how the classical brain looks like. It's just a simple PyTorch feed-forward network. There's two hidden ReLU layers, activation layers, and we're just taking those state features, and we output logits for each of the possible actions. Here's a visualization of that. So again, with those two input features going in, we have two hidden layers of 64 ReLU units each, and then we map those to 4 possible actions. This is also softmax at the upper layer that will convert those actions as logits into probabilities. Now in comparison, the quantum agent uses a parameterized quantum circuit, sensitive neurons and weights. We encode sensory features directly into the qubit rotation. So there's 3 gates. They're Rx, Ry, Rz. And as the circuit evolves, we naturally create superpositions and entanglements, and we allow qubits to represent multiple possible possibilities in parallel. And to train it, we use this parameter shift rule-based approach. So we run evaluations in batches against circuits, and then that's how we calculate gradients. And then finally, the parameters, those rotation angles, we update those with a learning rate, some regularization to prevent overfitting, and we also add a bit of random noise to encourage some exploration as well so it doesn't get stuck. And this is an example of building that quantum circuit using Qiskit, which is an open source library from IBM. So in short, it creates a parameterized quantum circuit where its sensory features are encoded as qubit rotations. Entanglement is added across layers, and then we do measurements at the end to produce classical actions. And this is a visualization of that circuit. So if you look down here, this is how we encode both chemical gradient strength and the direction. So the strength against an Rx rotation, the gradient's direction against an Ry rotation. And those parameters just flow through the rest of the circuit, and we add some entanglements, and then we measure the result at the end. I'm going to show some quick examples on how you can run these circuits on a simulator, an actual quantum computer, and then also on an actual quantum computer with error suppression. So we'll start this. This is using the AER simulator. So with this, you can run locally on a CPU or a GPU. We do something called transpiling with the circuit. We bind parameters, and then we execute the circuit there. The result is a set of bit string counts. So these are just simulated measurement outcome results. The real IBM hardware, it's pretty much the same, except we pick a quantum hardware backend to run the circuit against. So either one that we can preset ourselves, or we can kind of just use whichever machine is the least busiest. So structurally, it's the same as using a simulator, but now we need to take into account that there's also noise and other hardware constraints. So finally, this is very similar to before, but you can also run functions that can pretty much kind of do some pre-processing, post-processing to optimize the circuits and results. So you want to have these kind of processes happen to aim to reduce suppress errors, which would improve the circuit's fidelity, which means we can get better results faster with less shots. So we can run experiments faster. And shots means the number of times you run a quantum algorithm against a quantum hardware device. And this will be especially more useful as you kind of scale up, say this agent's brain. You might like adding more qubits or increasing the depth of these circuits, which would be especially useful when you might want to add more complex behavior than just feeding, such as evading predators, for example. All right, so now for the fun part, we can see the agent in action. So what I'll do is I'll just run a quick, short demo on a simulator. So I'm going to do that now. Is that coming up? Yep. It's pretty simple. This one was initialized with pretty decent parameters, so it finds a good learning strategy quite quick. Let's just let it run. It's just 10 epochs. Yes, so this is running in a quantum circuit simulator. So kind of averaged 40 steps. Yep. So I'm going to show another demo. This one's with a little twist. It's inspired by the many worlds interpretation. So the theory is that when a quantum system is measured, instead of collapsing into just one possible outcome, the universe branches out and all possible outcomes exist at the same time. So I will show an example of that. So yeah, this is kind of like every time the nematode makes a decision, it kind of branches out to different realities. And this is just, I think, capped at 18 times. Yeah. So just going to let that run for a little bit. Some of them will converge faster than others. But what I'll do is just go back to the presentation now. OK. So now let's go over the outcome of the project, mainly kind of benchmark classical and quantum approaches. So both scenarios use the same setup. We had a session with 20 runs or epochs. We kind of capped the amount of steps in each epoch to 300 steps. So if it hits 300, we cut it off if it doesn't find its prey. The environment size is just 10 by 10 grid in this case. There's 4 different spawn locations. So as you saw before, maybe you can spawn into 4 different corners, the worm, and then its food will just be in the opposite end. And 2 input features, the gradient ones, and the 4 possible actions, which is forward, turn left, turn right, or stay in place. So here's one instance of a result. Using the quantum circuits, it averages around 37 steps. And its success rate was 99%. So the first time it didn't find its food in those 300 steps, but after it was pretty OK. Here's the quantum one, classical approach. This one, average number of steps is 34. So pretty similar for 100% success rate. So this time it found it every single time. But if you look at it, the results are quite similar. There's a bit more volatility using the quantum circuits. And I'll explain why in a second. All right, so key takeaways. What did we learn from this? So first, Python makes it easy to kind of develop and do these kind of end-to-end simulations all in one language. Secondly, the elegans Nematode is a great toy brain with just 302 neurons. It's simple and interpretable, and it's also biologically inspired. Also, when we compare classical and quantum approaches, the performance, as you saw, was around the same, but the difference is in scale. So the quantum model only used 12 parameters, while the classical model needed about 4,600 for approximately the same performance. Classical training is faster than using a quantum simulator. In the quantum model, to get consistent results across sessions, you need to do more careful initialization of its initial parameters and also some extra tuning. So looking at its learning dynamics, classical agents were more stable, less noisy. Quantum agents, on the other hand, they're noisier because they inherently sample from distributions, which kind of give a more inbuilt exploration. And we found out that what matters most is not just the model, but it's also shaping the rewards well, designing efficient circuits or networks. One thing, though, to keep in mind is that noise on quantum hardware, when we ran this, is still quite a big challenge. But using tools like error suppression does help there. And finally, the big picture, quantum machine learning, it's still in early stages. But as current hardware scales, and we can simulate more complex models, I think that the potential is quite exciting. So looking ahead, there are a few exciting directions that this can go. First one is we could try to build better brains. So refine the design of these parameterized quantum circuits, improve the training methods, shape rewards better, so we can try to achieve more stable learning. Secondly, we can probably place these kind of agents into richer worlds. So instead of just a simple 2D grid, imagine larger, more complex environments, like 3D ones, with more challenging tasks. And beyond food seeking, we can add new behaviors, such as predator avoidance, reproduction, or expanding its sensory inputs, such as detecting temperature or using touch. Also, biologically, we could think about scaling up. So today we focus more on the nematode of 302 neurons, but eventually we can approach to more complex brains. For example, from the fruit fly, which is 140,000 neurons, or beyond that. But of course, progress also depends on better hardware. So as quantum devices get more powerful and error mitigation improves, we're able to run deeper, more meaningful experiments. And then finally, we can do more cross-benchmarking. So instead of just against classical neural networks, we can maybe also compare against neuromorphic type designs, which are more brain-inspired, and other type of models. So you can get a better idea of where these quantum algorithm approaches fit in. And then finally, I'm just going to go through some sources we can both learn and practice in the space. All right, so learning, there's a lot of sources out there. My company provides courses which we call Black Opal. I'll get into that more in a second. There's also Qiskit from IBM. They have their own textbook, so you can learn how to use Qiskit. There's also Penny Lane, which has a lot of tutorials on quantum machine learning. A lot of books out there and online courses. There's Coursera, edX, and others have these. There are communities out there. There's Reddit has a subreddit called Quantum Computing. Also, Qiskit have their own Slack. On the practice side of things, there's a number of platforms out there. Qcontrol provides access to these backends as well, but with error suppression built in. But the other platforms out there, big ones are from IBM, Microsoft, Amazon. There's quite a lot of open source projects out there. Some of them are from Google, NVIDIA, Penny Lane. All right, it's going to touch a little bit more on Black Opal one from Qcontrol. So we have interactive courses to learn quantum computing. And each first part of each course is free. Also, there's also a coupon, PyCon 25, if anyone wants to access all the courses. And also, if you want to run programs on a real quantum hardware, IBM has a lot of machines available throughout the world, and they provide 10 minutes of free access per month. Otherwise, it's very expensive to run them. It's, I think, $100 per minute. Yeah. Yeah. All right, and finally, this project that you just saw is open source now. So if you want, you can try it out for yourself, fork it, or contribute to it. So you can just clone it from that link or scan that QR code. That's it. Thank you.
Thank you, Chris. We have time for one question. Does anyone there?
Hi, Chris. Excellent talk. So my question is about the architecture of the neural network that you show.
Yep.
Like with two hidden layers for the multi-layer perceptron.
Yep.
So how do you choose that one? Is that biologically motivated, in this case by C. elegans, or how do you determine how many layers you have to have?
A lot of fine-tuning, like I tried with 1 layer, 2 layers, 4 layers, adding less hidden parameters. Around 64 layers, no, 2 layers, with 64 other units, it started to hit around the same formats. Any less than that, less parameters, it takes too long to converge to learning strategy. I think too much, it seems to be overfitting and just learning really, really fast. So it's just a lot of trial and error in that case. So it's not really inspired by Nematode's brain. It's probably just like a simple input, hidden layers, outputs kind of model that tried to get similar results to the quantum circuits one.
Thank you. Thank you,
All right.
Chris, for your talk
Thank you.
and coming here to PyCon today.
Awesome. Thank you. Thank you very much. My pleasure.
That's it.